PIC10F200. The PIC10F200. Oh, PIC10F200. The PIC10F200. Whoa, wait, it doesn't go in your mouth. Microcontrollers are not tasty. Tweedledee, smash the like and subscribe. Bro, 2-bit electronics. Ooh, mama, 2-bit electronics. Yabba dabba, 2-bit electronics. Oh, 2-bit electronics. Wow, wow.
Thank you for watching my video. I have made an entire playlist on my channel where I store all of my PIC10F200 videos. I have made 20 videos and counting. So today the video I am making is on a program I created, and it's using Timer0 as a delay. I've been excited to create this one for a while because in other code examples the delays require inner and outer loops and setting up counters. So I was really excited to try using Timer0 within the delay because I think it's making more use of the technology within the chip, that being Timer0, and it's a little bit easier on the eyes. This block of code looks simpler than delays I have used previously. So I will just read the code and explain it as you see it. So I gave it a title, using Timer0 as a delay. Then I have included the header, or rather the PIC10F200 library of instructions and the things that are specific to this chip. And I have it configured. I won't go into that. I've covered that enough in previous videos. I defined GP0 pin. Here it is here. It's pin 5. I've defined that as LED, as that's the pin on my breadboard setup that I have set up using an LED. Here's the start of the program. I'm setting up the trace register, setting GP0 as an output, and I set the rest of the 3 pins as input, although it doesn't really matter for this particular program. And I have also set the prescaler. Page 16 of the datasheet shows the prescaler, particularly bits 0, 1, and 2. Here they are here. And without digressing into explaining how the prescaler works, when you set the bit values as 1, 1, and 1, it gives the greatest Timer0 rate. So for every internal FOSC, or frequency oscillation, of the chip, you get 1 timer pulse added to the clock. So the timer rate is slowed down the most when the prescaler bit values are set to 111, and that will set these 3 bits of the option register. The internal clock is chosen, so it's set to 0 as well. I set these as 1 and 1. I disabled these. They're not really necessary for this program anyway, and my circuit board setup. And this is important. Bit 3 is set to 0 because you want the prescaler, which is what you set the bits down here as, you want the prescaler assigned to Timer0. not the watchdog timer. So setting bit 3 to 0 is pretty important. So once again, I set the prescaler to 111, and the prescaler assignment bit is set to 0. Anyway, then that's moved to the option instruction. Of course, you don't see a move WF. Putting this value into the option is because specific to this library, I suppose, the trace and the option text you see on the screen is actually an instruction. And it even explains that here in the datasheet, this sentence. So once again, I'm not getting very creative in my circuit board setup and my projects, but this is another Blink program. But the point is not to create a Blink program, really. It's just to show that I created a delay with the use of Timer0. So I set it on, then I call a delay down here, then it returns back up here, then it clears the LED bit, which is GP0. I set that up here. And then it calls the delay, and it returns back, and it says go to main, and it starts all over again. So the thing I'd really like to showcase in this video is making use of Timer0 as a delay. So I started out, when the delay is called, I started out by clearing Timer0. Now really what's necessary is some good thorough study of the Timer0 module. Not only that, but you should study the timer module alongside the option register, and a good study of the prescaler will help you understand why this code is working the way it does. And I spent 2 hours studying the datasheet, and you can find those videos in the description below. I'll link them there. And they're basically just me grumbling and studying how these things all relate to each other. But this video would be too long if I had to explain that. In my own words, and I could be wrong in technical detail, but basically, the Timer0, when you enable it, and you do that with bit 5 of the option register, in fact, you specifically choose the internal instruction cycle clock rather than setting GP2 as the external input clock. So this is important to set as 0. But anyway, I already covered that up here. But anyway, when you set the timer to 0, it automatically increments every time there's a completion of an instruction cycle. Further, it will be slowed down when you use the prescaler, which we set to 1 to 256. So it's going to slow the timer count even more through the use of the prescaler. Okay, so now you clear the timer, and in the delay loop I have moved the value written in hexadecimal, but this is the value 255 in decimal, and I've loaded the working register with that value. And then the next line I've used the sub WF mnemonic operand, what do you call those? Opcode instruction. I've used the sub WF instruction to subtract this file value from the working register, because that's what this code does. It subtracts this file from the working register. The working register was loaded with what? 255. Initially, Timer0 was cleared, so it's a value of 0. So the first iteration through this delay loop, you're taking the timer value of 0 and you're subtracting that from 255. And then you're storing the value back in the working register. So 255 minus 0 is 255. So then it'll move to the next line of code, bit test file skip if set. And what file is it going to test? It's going to test the status register. If you don't know how the status register works, well, let's have a look. Here's the status register. This is the 0 bit. It's bit 2, 0, 1, 2. It's bit 2. And it will get flagged with a 1 when the result of an arithmetic or logic operation is 0, which is a little bit ironic in a way. Like, so when an arithmetic operation becomes 0, the 0 bit becomes 1. But that is how the status register works. So anyway, let's start it back up at the top. So when we move a literal value into the working register, we move 255 into the working register, and we subtract Timer0 from the working register. That's how sub WF works. Initially, this is set to 0, and this is set, the working register is set to 255, so 255 minus 0 is 255. Then we bit test the file, and we skip if it's set. So 255 minus 0 equals 255. So the 0 bit is not set. The arithmetic operation that happened here is not a 0 result, so this won't be set. So skip if set, it's not set. So it won't skip this next line. It'll execute this next line, which is go back up to the delay loop. Now we move 255 back into the working register, and we subtract the file from the working register, and that TMR0 now will probably be 1, assuming one cycle happened. Who knows exactly what the value is? Let's assume it's 1, and then it'll bit test that. Is the 0 bit set? 255 minus 1 equals 254. Nope, the 0 bit is not set. That arithmetic operation did not equal 0, so the Z bit is not set. So it'll go back up to, it won't skip the next line, it'll go to the next line, go back up here, and it will iterate until finally the WReg equals 1, and then 1 is subtracted from that, and then it'll bit test file skip if set, and eventually the Z bit will get set because the arithmetic operation will equal 0. So it'll skip the next line if it's set, and it'll go to return. I used to use the return instruction, but MPLAB doesn't like that, so now I'm using the retlw, return from subroutine, and it'll go back up into wherever the delay was called from, and then it'll bit clearf, or whatever the case may be. But that's how this delay routine is working. Okay, hopefully that explains things, but I'll go through it once again just reading my comments. So this is a program using Timer0 as a delay. I set GP0 up to an LED, and I called that pin the LED pin. Here's the initialization. I set GP0, or the LED pin, as an output. I set the prescaler to the maximum value, and that's another thing I should mention. If you want to experiment with the prescaler, here it is here, and you want to speed it up, you can change the prescaler value to say 1 110. If you set it to 000, it won't even be a blinking LED program anymore. It'll be iterating so quickly that the human eye will not perceptibly be able to see a blinking LED. So what I recommend is just try changing the prescaler value from 111 to 110 and try uploading your code and testing the difference. Recommendation is try changing this to 110, clean and build your code, upload it to your device, and if you change it to 110, the prescaler is set to a faster rate and the LED should blink faster. Currently it's set to the slowest prescaler rate that the Timer0 is making use of. Okay, then the main loop, this is the blink program. Turn the LED on, call the delay, turn the LED off, call the delay, repeat the loop. I'll get rid of this. I'll get rid of the comments. It's obvious what it's doing. Here's the delay subroutine using Timer0. Clear Timer0 register. Load the working register with 255. Subtract the file from the WReg. And this file happens to be Timer0, and this will continue to increment as time progresses into the future, and every cycle of the internal oscillator of the microcontroller will add a 1 to this every cycle. So this will automatically increase in value, and because there's a prescaler, it slows things down a little bit. Subtract the file from the W register. Initially this would be 255, which was loaded into the working register, minus the value of this file. Well, it was cleared initially, so the value should be 0. So the first iteration through this loop, it will be 255 minus 0. Then it will check if the 0 flag is set, and it won't be set until it iterates through this loop and it creates a 0 value when this line is executed. While the 0-bit flag is not set, it'll go to delay loop and continue to iterate, but when the 0 flag bit is set, it will break out of the loop and it'll return from the subroutine, which will send it back up into the blinking of the LED. Okay, hopefully that explains how Timer0 is being used as a delay in this program. What follows will be a little video clip of what it looks like on my PIC10F200. Thank you very much for watching, and hopefully this shows a great new way or different way of creating a delay within your code. Thanks for watching, and please check out everything else that's on my channel.
The PIC10F200, oh, PIC10F200, the PIC10F200. Whoa, wait, it doesn't go in your mouth. Microcontrollers are not tasty. Tweedledee, smash the like and subscribe. Bro, 2-bit electronics. Ooh, mama, 2-bit electronics. Yabba dabba, 2-bit electronics. Ooh, ah, 2-bit